There's this absolutely fantastic, pragmatic reality check from the brilliant statistician George Box. He said, all models are wrong, but some are useful. And honestly, that perfectly sets the stage for our topic today. The universe is just incredibly complex, right? Any mathematical model we build is literally just a simplified approximation of reality. The goal isn't to build some flawless replica of the world. The goal is to build something useful. But that begs the question, how do we actually know when our model is useful and when it's just plain wrong?
Welcome to The Explainer. Today we're diving deep into topic 5.4, underfitting and overfitting. We're going to diagnose exactly why machine learning models fail in the real world and, more importantly, how you can fix them. We're looking at the two extreme ways a learning algorithm can completely miss the mark.
So here's our roadmap. First, the goal of a model. Then underfitting, which is the simple model. Next, overfitting, the complex model. Fourth, we'll hit the bias-variance trade-off. And finally, regularization and solutions. Let's get into it.
Okay, Section 1. The goal of a model. Predicting the unseen. Before we can fix a broken model, we have to agree on what a working model actually looks like. And this is really the golden rule of machine learning. The ultimate test of a model is predicting new, unseen data. It is not simply memorizing the training examples it's already seen. Think about it like a student studying for a big exam. A trivial algorithm could just perfectly memorize the practice test, right? It would score 100%, making 0 mistakes. But if you handed that student a completely new exam with different questions, even if they covered the exact same concepts, they'd fail miserably. In practice, a model that merely memorizes its training data is completely useless. What we really want is solid performance on a holdout set, which is data the learning algorithm never even saw during training. When you map out this whole journey of model training, you really see three distinct scenarios. On one extreme, you have a rigid, straight, linear model trying to fit data that clearly curves. It just misses the pattern entirely. On the completely opposite extreme, you have this wildly squiggly curve that perfectly hits almost every single data point, but its overall shape is just completely erratic. And then, right in the middle, you have a smooth curve that captures the general trend of the data without obsessing over every single little dot. That middle ground, that's exactly our target. That is what we call the good fit.
Section 2. Underfitting. The simple model.
Let's look a little closer at that first extreme scenario, a model that is just too simple. The crucial point here is that high bias is the formal statistical term for underfitting. It's a really important term to remember. High bias means your model fundamentally failed to learn the underlying pattern. It's heavily biased towards its own overly simplistic assumptions. If your model is making a ton of mistakes on the exact same data you use to train it, well, you've got a high bias problem. It's kind of like trying to understand a complex Shakespeare play by only learning the alphabet. You're just not capturing nearly enough complexity to get the job done. So, why does this happen? There are really two main culprits here. First, your model might simply be too rigid. Like we said, using a straight linear model for data that naturally curves is always going to underfit. Second, the features you provided might just completely lack predictive power. Imagine trying to predict whether a patient has cancer using only their height, their blood pressure, and their heart rate. It honestly doesn't matter how great your algorithm is, those features simply do not contain the right information to make that prediction. To fix underfitting, you have to add complexity. You either step up and choose a more advanced model, or you get to work engineering better, more informative features.
Now let's totally flip the script. Section 3. Overfitting. The complex model.
What happens when your model is entirely too complex? Imagine a polynomial regression of degree 10. This thing will contort itself wildly, bending sharply up and down, doing whatever it takes just to perfectly intersect almost every single training dot. Sure, it predicts the training targets perfectly, but imagine bringing in a brand new data point that sits just slightly to the left or right of the existing ones. This wild line is going to make massive, catastrophic errors on that new data. It has completely lost the plot. The formal term for this erratic, overfitting behavior is high variance. High variance means your model is extremely sensitive to small fluctuations and noise. Think of it this way. If you were to sample a slightly different set of training data from the exact same source, a high-variance learning algorithm would spit out a drastically different model. It basically changes its mind entirely based on the slightest breeze in the data. Overfitting happens when a model acts like a giant sponge. It soaks up everything, including the harmless noise and the weird, specific idiosyncrasies of your small training set, instead of learning the actual broad pattern. If you try throwing a massive, deep neural network or a very tall decision tree at a relatively simple problem, it is going to overfit. Alternatively, if you have thousands of features but only a few dozen training examples, you're giving the model way too much freedom. It will mathematically contrive some bizarre way to connect those features to the output, even if it's pure random coincidence.
Section 4. The Bias-Variance Tradeoff. This right here is the core tension in all of machine learning. It all crystallizes into this incredibly delicate balancing act. On one side, you have high bias. Your model is too simple and it outright ignores the actual data pattern. On the flip side, you have high variance. Your model is too complex and it just memorizes the random noise. You have to carefully balance not being simple enough with being entirely too complex. Because here's the catch. As you decrease bias by making your model more powerful, you are almost always increasing its variance. Finding that sweet spot in the middle, that good fit, is really the art and the science of this entire field.
Okay, Section 5. Regularization and Solutions.
So, how do we actually treat a model that has swung way too far into high variance? Let's build out your troubleshooting toolkit. If your model is overfitting, you want to systematically work through these steps. Step 1, simply try a less complex model. Downgrade from a polynomial to a linear kernel, or maybe use a shallower decision tree with fewer layers. Step 2, reduce dimensionality. Strip away any features that aren't strictly necessary. Step 3, feed the beast. Add more training data if you can possibly get it, because more data smooths out the noise. And finally, Step 4, regularize the model.
Regularization is arguably your single most powerful treatment. It's essentially an umbrella term for methods that mathematically force the learning algorithm to build a less complex model. It physically stops the algorithm from assigning massive, non-zero values to tiny dimensions just to perfectly hit every single noisy training point. When you apply regularization, you are intentionally accepting a slightly higher bias, meaning, yeah, you might make a few more mistakes on your training data, but the payoff is a massively significant reduction in variance. The model becomes stable, it becomes generalizable, and most importantly, it becomes actually useful in the real world. I want to leave you with this final thought to keep in mind the next time you're sitting down to build a model. How will you balance simplicity and complexity to find that perfect good fit in your next dataset? Because remember, if you find yourself obsessively chasing 100% perfect training accuracy, it almost always means you've built something totally useless for reality. You've got to embrace the trade-off, use those regularization tools, and build a model that doesn't just memorize the past, but can actually understand the future. Thanks for joining me for this explainer.